Hi there, this is Heath, and we're starting week 8. These are the notes on synthetic division and diagonalization. Let's go ahead and get started. This is a review from what we learned in week 7. Let A be a square matrix. We modify A by subtracting the value lambda from the diagonal. Then the determinant of this matrix, if we set it equal to 0, gives us the eigenvalues of A. Let's just review an example. If I want to find the eigenvalues of this matrix, I will change this matrix to 6 minus lambda, -1, 6, and 1 minus lambda. Calculate the determinant of this matrix, and that's going to be multiplying 6 minus lambda times 1 minus lambda, and then subtracting the product on this diagonal. And then this requires multiplying two binomials together. This is lambda squared minus 7 lambda plus 6, minus -6 is plus another 6, which is lambda squared minus 7 lambda plus 12. That factors into lambda minus 3 times lambda minus 4. And so the eigenvalues are 3 and 4. I want to talk about this formula that we got right here. This is called the characteristic polynomial of A. The roots of the characteristic polynomial, the values that give it 0, the characteristic polynomial's roots, are the eigenvalues of A. We'll look at the characteristic polynomial more in a little while. We found the eigenvalues. To find the eigenvectors, we have to undergo a procedure for both eigenvalues. What we'll do is we'll replace lambda in this modified matrix by each value that we found. 6 minus 3 is 3, and 1 minus 3 is -2. And then we'll augment with zeros. So what we did here was we replaced lambda with its numeric value. We augmented with zeros. And now we're going to row reduce. This is easy to row reduce. Row 2 minus 2 row 1 gives me 3, -1, 0, 0, 0, 0. And if I divide the top row by 3, I get 1, -1/3, 0, 0, 0, 0. And this leads to the equation x1 is equal to 1/3 t, and x2 is equal to t. And that's the same thing as t times the vector 1/3, 1. And so one of the eigenvectors, when lambda is equal to 3, the eigenvector is 1/3, 1. When lambda equals 4, well, we need to figure that out. I'm going to do the same thing again. Replace lambda with 4. 6 minus 4 is 2. And 1 minus 4 is -3. Augment with zeros. And then row reduce. I can get rid of this 6 by taking row 2 minus 3 row 1. 6 minus 6 is 0. -3 minus -3 is 0. 0 is 0, 0. and then divide row 1 by 2. And this is almost what we did over here, except that we have a 1/2 instead of a 1/3. x1 is equal to 1/2 t, x2 is equal to t, and so that gives us the vector 1/2, 1. And so that's how we found the eigenvectors for A. And if we have the eigenvalues and the eigenvectors, we can calculate expressions involving powers of A. In fact, this is one of the most important uses of eigenvalues and eigenvectors, is to be able to calculate expressions involving taking a power of a matrix. The first step we're going to do is to write 2, 5 as a linear combination of the eigenvectors. And that turns out to be 3 times 1/3, 1, and 2 times 1/2, 1. 3 times 1/3 is 1, 2 times 1/2 is 1, 1 plus 1 is 2, 3 times 1 is 3, 2 times 1 is 2, 3 plus 2 is 5. So this combination works. Multiply the combination by a to the k. So 6 to the negative 1, 6 negative 1, 6, 1 to the k times 2, 5 is the same thing as 6 negative 1, 6, 1 to the k times this combination. And then here's where the magic happens. On the right side of the equation, I can replace this matrix with lambda. But I have to replace it with a different value of lambda for each eigenvector. Can replace A with lambda on the right side. And so the first term will be 3 to the k times 3 times 1/3, 1. And the second term will be 2 to the k times 2 times 1/2, 1. And this is now just calculating all this out. 3 to the k, 3 and 1/3 cancel, so I just get 3 to the k. 3 to the k times 3 times 1 is 3 to the k plus 1, plus 2 times 1/2 cancel, but I still have 2 to the k, and 2 to the k times 2 times 1 is 2 to the k plus 1. And so this expression and this expression are equal. Okay. So I want to start looking at finding eigenvalues for some larger matrices. And this is a special case. This is an easy special case, but it's a special case that we're going to start with. So the goal is to find eigenvalues of matrices bigger than 2 by 2. This is a special case. But I want to start with this special case. The way we would find the eigenvalues is to subtract lambda from the diagonal. So a minus lambda I would be 5 minus lambda, and then a bunch of zeros. Negative 7 minus lambda for this entry. 19 minus lambda for that entry. 1 minus lambda for this entry. And 4 minus lambda for this entry. And then we want to calculate the determinant of this matrix. Well, this matrix is an echelon form, so we can multiply down the diagonal. And then solve this equation. Well, this equation is already factored for us. Lambda is equal to 5, lambda is equal to negative 7, lambda is equal to 19, lambda is equal to 1, lambda is equal to 4. So in this special case, our diagonal led to a determinant that was already factored out for us, and it made it easy to find the eigenvalues. In fact, the eigenvalues are the entries that are on the diagonal. But most matrices are not already set up in this form for us. And so a question I want to look at in the rest of this video is, what if the characteristic polynomial does not factor easily? We're going to use a technique called synthetic division to help identify correct factors. You may have seen synthetic division in a previous class, in which case the rest of this video is going to be review for you, and that's okay. So what if this was our characteristic equation, and we want to find the eigenvalues for this matrix? That means we need to be able to factor this. Based on the fact that the constant term is negative 10, then we might try the factors that go into negative 10, which are plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And we will test these values to see if they work. We're going to start out by testing an incorrect value to see what happens. Okay? So we're going to try lambda equals 2, and I'm going to go ahead and let you know lambda equals 2 is not an eigenvalue. But I want to show you what happens. Here's how we test it. I'm going to write the coefficients of the polynomial in a row listed in descending order of degree. So the cubic term is 1 lambda cubed, negative 2 lambda squared, negative 13 lambda, negative 10. If I have to, I will insert a 0 as a placeholder if any of these terms are missing. The 2 is the number that we're testing. And here's how we test the 2. We initialize the process by just copying the leading coefficient down to a second row. I'm just going to take that 1 and just bring it down here, not do anything with it. But from here on out, I'm going to multiply and add to the next column. Let's say multiply, then add to the next column. So 1 multiplied by 2 gives me a positive 2, and then I'm going to add that to the next column, and that gives me a 0. And then I'm going to repeat this process. 0 times 2 is 0, so that'll go up here. And then add that to the next column, and that gives me a negative 13. And then negative 13 times 2 is negative 26. Add that to the last column, and that gives me a negative 36. So we copy the leading coefficient down just to get us something to start with. And then from that point on, we multiply and add, multiply and add, multiply and add. If our total is not a 0, then this is not a correct solution. This is not going to be an eigenvalue. So lambda equals 2 does not work. So let me show you one that does work. Let's test lambda equals 5 and see what happens. Again, I'm going to start by copying down the coefficients. And I'm testing lambda equals 5. I start the procedure by copying the 1 straight down. And then from that point, I multiply by 5 and then add to the next column. So 1 times 5 is 5, and negative 2 plus 5 is 3. 5 times 3 is 15. Negative 13 plus 15 is 2. 2 times 5 is 10. Negative 10 and positive 10 is 0. That makes me happy. And so lambda equals 5 is an eigenvalue. This table is summarized right here on the next page. We said at the beginning of this process that negative 10 gave us these values to test. And we tried positive 2, and that didn't work. And we tried positive 5, and that did work. Do we need to keep trying all of the other values that are on the list? And the answer is no. Not only does this process confirm that we have an eigenvalue, but the other numbers in the bottom row tell me how to find the rest of the eigenvalues. 1, 3, 2, if I convert this back into a polynomial, is lambda squared plus 3 lambda plus 2, and that factors into lambda plus 1, lambda plus 2, and so the other eigenvalues are negative 1 and negative 2, and we don't have to do any more work. Once we have this term here, the remaining coefficients give me a smaller polynomial that I might be able to factor more easily. And so now we know all 3 eigenvalues. They're positive 5 and negative 1 and negative 2. Let's do one more example. Let's show that lambda equals 4 is an eigenvalue of a matrix that has this characteristic equation. And then we're going to find the other 2 eigenvalues. So I'm going to start by copying the coefficients down. 1, negative 4, positive 9, negative 36. I'm testing the 4. I begin the test by copying the 1 straight down. And then from that point on, I multiply and add. Negative 4 and 4 is 0. 0 times 4 is 0, so that gives me a 9. 9 times 4 is 36, and that gives me a 0 again. So 0 shows that lambda equals 4 is an eigenvalue. But the other 2 come from this equation here. Lambda squared plus 0 lambda plus 9. And this doesn't factor. It's lambda squared equals negative 9 and lambda is equal to the square root of -9, and that's imaginary. It's 3i and -3i. Yikes. It is possible for a matrix to have a complex eigenvalue or an imaginary eigenvalue. These can happen. Next week, we'll look at imaginary eigenvalues in more detail, but this is something that can happen. All right, we're back. Let's compute the eigenvalues and eigenvectors for this matrix. The first thing we're going to need to do is find the characteristic polynomial. That is, we need to find the determinant of this matrix here. 1 minus lambda, 2, 0, -1, -1 minus lambda, +1, 0, 1, and 1 minus lambda. There are a couple of ways that we can do this, but let's try cofactor expansion down this column. This is going to be 1 minus lambda times the cofactor in the 1, 1 position, plus -1 times the cofactor in the 2, 1 position. And then there's a third term, but it's 0 because of this term here. And so that's 1 minus lambda times the determinant. If we cross out the first row in the first column, we've got these 4 entries left. -1 minus lambda, 1, 1, +1 minus lambda. 2 plus 1 is odd, so I change the sign of the -1 and make it a +1 times the determinant. And then this time, if I remove the first row and the first column and the second row, I'll get 2, 0, 1, 1 minus lambda. And that's 1 minus lambda times -1 minus lambda, +1 minus lambda, -1, plus 2 times 1 minus lambda, -0. The other direction is -0. I'm going to use a little trick here. I'm going to take this 1 minus lambda and this 1 minus lambda and bring it out to the front. And what I'm left with is -1 minus lambda times 1 minus lambda minus 1 plus 2. All right, we're going to FOIL this out. And this gives me first times first is -1. Outer is plus lambda. Inner is minus lambda. And then last is plus lambda squared. -1 plus 2. Some cancellation happens here. Plus lambda and minus lambda cancel. And we're left with lambda squared -1 plus 2. Those cancel. So we have 1 minus lambda times lambda squared. So we subtract lambda from diagonal, we find the determinant here. This is just writing out the steps that we did before. We get 1 minus lambda times lambda squared. And so the roots are lambda equals 1, and lambda squared, that's lambda equals 0, and lambda equals 0 a second time. The eigenvalue lambda is equal to 0 is a double root for this determinant. And we say that it has, this is just fancy terminology, but it's terminology we have to understand. We say that it has an algebraic multiplicity of 2. Algebraic multiplicity is how many times lambda is a root of the characteristic polynomial. In this case, lambda equals 0 has an algebraic multiplicity of 2. It's also true that lambda equals 1 has an algebraic multiplicity of 1. Because it was a single root, but we normally talk about multiplicities that are greater than 1. But we usually talk about okay. So we still need to find the eigenvectors. And we have to do this for lambda equals 1 and for lambda equals 0. When lambda is equal to 1, we take 1 minus 1, which is 0, negative 1 minus 1, which is negative 2, 1 minus 1, which is 0. I'm subtracting 1 from the diagonal entries. All the other entries stay the same, and I augment with zeros. Subtract lambda from the diagonal. But I have a numeric value for lambda. So there's no variable at this stage, and augment with zeros. This system turns out to have only one free variable, and this is a solution. But let's walk through the process of finding this. If I try to row reduce this, what I might do is bring this negative 1 to the top row and change the sign, make it a positive 1. So I'm going to rearrange some stuff here. 1, 2, negative 1, 0, 0, 2, 0, 0, and 0, 1, 0, 0. This row and this row are almost multiples of each other. We'll take row 2 divided by 2, and then row 3 minus what we just had, row 2 divided by 2. And we get 1, 2, negative 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. And then finally, I'm going to get rid of this 2 up here, row 1 minus 2, row 2. I get 1, 0, negative 1, 0, 0, 1, 0, 0, 0, 0, 0, 0. I have a leading entry in column 1, a leading entry in column 2, but column 3 is free. And so my equations are x1 is equal to t, x2 is equal to 0, and then x3 is also equal to t. And so that's t times 1, 0, 1, and that's where we get our solution vector. When lambda is equal to 0, we solve this system. This system has exactly one free variable also. Solution vector is 2, negative 1, 1. We're going to solve this system the same way that we did before. We subtract 0 from the diagonal, which doesn't change the system at all. Augment with zeros, row reduce, and then find what our solution vector is. Let's try computing the eigenvalues and eigenvectors for this matrix. The row reduction is pretty nice here. So first thing we're going to want to do is find the characteristic polynomial, which means we need the determinant of -1 minus lambda, 0, 1, 3, 0 minus lambda, -3, 2, 0, -2 minus lambda. And I'll do a cofactor expansion down this column. So this is going to be negative lambda times the cofactor in the 2, 2 position. And that's the same thing as negative lambda times the determinant of this matrix. -1 minus lambda, 1, 2, -2 minus lambda. -1 minus lambda, -2 minus lambda. Minus 2 for the other diagonal. When we FOIL this out, -1 times -2 is +2. -1 times negative lambda is positive lambda. Negative lambda times -2 is +2 lambda. And negative lambda times negative lambda is lambda squared. And then there's a -2 here that cancels out with the +2. And so we have negative lambda times 3 lambda plus lambda squared. This is our characteristic polynomial. Negative lambda times 3 lambda plus lambda squared. Well, if we set this equal to 0, I can take out a lambda from here. So we get negative lambda times 3 plus lambda. And so my solutions are 0, 0 again, and -3. And so 0 has an algebraic multiplicity of 2. And again, -3 has an algebraic multiplicity of 1, but we generally call attention to multiplicities that are higher than 1. So these are the eigenvalues. For the eigenvectors, we have to check lambda equals 0, and we have to check lambda equals -3. For lambda equals 0, we subtract 0 from the diagonal, which does nothing, and augment with zeros. I'll cancel out the 3 and the 2 here. Row 2 plus 3 row 1, and row 3 minus 2 row 1 gives me -1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then change the sign in the top row, negative row 1. We only have one leading entry. There's a leading entry in column 1, and then we have 2 free columns. So if I assign S to the second column and T to the third column, the top row says that x1 is equal to T, x2 is equal to S, x3 is equal to T. T is multiplied by 1, 0, 1, but S is multiplied by 0, 1, 0. And so we have 2 different and linearly independent eigenvectors for lambda equals 0. Lambda equals 0 gives 2 free columns, eigenvectors are 1, 0, 1 and 0, 1, 0. We say in this case that lambda equals 0 has a geometric multiplicity of 2. Algebraic multiplicity is how many times lambda equals 0 was a root of the characteristic polynomial. Geometric multiplicity is equal to the number of free variables in a minus lambda I equals 0. In this case, we had 2 free variables in the homogeneous equation, and so the geometric multiplicity is equal to 2. We'll see this definition on a slide in a moment, but this time we have an algebraic multiplicity and a geometric multiplicity for this eigenvalue. To continue on, let's go through lambda equals -3. I'm going to subtract -3, which is the same as adding +3 to each of these terms. -1 plus 3 is 2, 0, 1. 3, -3, and then 2, 0, and 1 again. Augment with zeros. The top row and the bottom row cancel. And I'm also going to go ahead and divide the middle row by 3. I'm going to switch these 2 rows. And clear out this 2, row 2 minus 2, row 1. So 2 minus 2 is 0. 0 minus 2 is -2. 1 minus -2 is +3. 0, 0, 0, 0. So 2 minus 2, 0 minus 2, -1 minus -2. Now I'll get a 1 here, and then use it to clear out this 1 over here. Math is going to get a little bit messy, not by too much. Row 2 divide by -2 gives me 0, 1, -3 halves, 0. And then row 1 minus row 2 gives me 1, 0, -1 minus -3 halves is +1 half. And I have one free column here. x1 is equal to -1 half t. x2 is equal to +3 halves t. x3 is equal to t. And so my second vector, lambda equals -3, has one eigenvector. And it's -1 half, +3 halves, and 1. Okay? So some definitions. If we find that lambda minus k to the m power is a factor of this determinant, and m is the largest power that this is true for, then we say that k is an eigenvalue with an algebraic multiplicity of m. Algebraic multiplicity is, again, how many times the eigenvalue is a root of the characteristic polynomial. But if we find m linearly independent vectors satisfying this equation, then we get an eigenvalue with what we call geometric multiplicity m. As it turns out, and we won't prove this, but there's a fact, the algebraic multiplicity is always greater than or equal to the geometric multiplicity. They can be the same, but if one of them is larger, it will always be the algebraic multiplicity. We'll use these multiplicities to answer a question about eigenvalues in the next set of slides. Thanks.